So this is joint work with Yukai Song and Changliang Wang. And Changliang will give the next talk. So here's the outline of the talk. First of all, I will review the classical positive mass theorem and its connection with the existence positive scalar curvature metrics, and then talk about motivations for singular metrics, and then state the main results, and last will indicate the ideas of proof. Okay, so the positive mass theorem motivated from the general relativity can actually be stated as a purely geometric result, and as such is one of the most important results about scalar curvature. And it concerns a class of non-compact manifolds, which are called asymptotic flat manifolds. And these are the spaces which looks like a Euclidean space at infinity. So in other words, outside a compact set, your space will look like a Euclidean space outside a ball. And moreover, the metric will look like a Euclidean metric as well, up to some error, which is decaying fast, and up to a power of which is referred as the asymptotic order. And this asymptotic order is generally assumed to be bigger than n-2/2. Okay. In addition, we assume, one usually assume the scalar curvature is integrable. So we'll see why this assumption is here. Just a bit. So in picture, so the space will look like something inside, and then, but at infinity, you have asymptotic looks like a Euclidean space. So that's the basic picture. And associated with such spaces, one has the so-called the ADM mass. Okay, and so this quantity is defined by what's called the flux integral at the sphere at infinity. So involving the first derivative of the metric information. Okay, so xi here is the Euclidean coordinate at infinity, and you're taking the partial derivative with respect to that specific Euclidean coordinate, and so you're integrating over a sphere, a large sphere at infinity.
May I ask you a question?
Yes.
Because so this condition essentially says that there is an infinitesimal perturbation. So when you go very far away, it's just metric of the sphere and small perturbation of the metric around the sphere, right?
Yeah,
right?
Exactly.
Okay, but then you know that granted this condition, there is actually by linear analysis, by perturbation, it was done by in Wang, Schoen-Yau, and then Blokamp. It's actually, you can extend this metric when it become actually spherically symmetric. So it will be Schwarzschild, right?
Mm-hmm.
So you don't need maybe for rigidity it's essential, but for positive mass theorem you can assume metric is just spherical and it just grows slightly faster or slightly slower your mass than flat case. It expands, so it expands in the first order of magnitude like Euclidean, and the second order smaller or faster. And you don't need any integral, you can say it in words, right? So I can forget
Yeah, that's correct. Yeah,
right.
yeah.
So you can
You
forget all
got
this.
it.
However, and then there is extra point. But the moment you formulate it in this form, you don't need second first derivative of the metric. It's just the metric itself must be closed. At this
That's
moment, you have better theorem, and it follows then from, at least for, in the spin case, it follows from the this. Or should I forgetting the names? Yeah, these two guys who generalize LaRule theorem. Yeah, actually, in this case, LaRule theorem is sufficient. Actually, LaRule theorem here is good enough. Yeah, it follows from LaRule theorem, and you get better result. My question is, if you go back instead of this perturbation, what would be the better condition there? So this is a traditionally physicists do that for their reasons, but from geometric point of view, it's super artificial condition, right? And the question is if there is a theorem incorporating these two, the one which you said when you have asymptotically flat non-spherical, or not spherically symmetric, or at infinity it is spherically symmetric, but there you need kind of, instead of first and second derivative, only zero derivative. Is there such formulation?
As far as I know, I don't know such. Yeah. So according to result of Schoen-Yau, the metric look like what's called the Schwarzschild metric plus the error term. So Schwarzschild is spherically symmetric and up to, so it's up to some order, but
no, but I'm saying no. This is what I said, of course. By Schoen-Yau and in a better form actually by Lockham, there is
yeah.
you can reduce to this very special case when metric is symmetric, right? And that becomes Schwarzschild, essentially Schwarzschild, and this through kind of very simple general perturbation result. But then the moment you know it's symmetric, you don't need first or second order. The metric must be just approximately spherical. Actually, you don't know exactly it is, yeah, because it follows from LaRue theorem, right?
I actually am not sure whether Locam's result can actually get you to be exactly Schwarzschild
No, but
because
spherically symmetric. The moment it's spherically symmetric, this material that becomes OGE equation to go to Schwarzschild. If it's spherically symmetric, it actually doesn't have actually we need less than spherically symmetric. It must be warped geometry or something. So this you can.
right. Mm-hmm.
The moment you reduce, if you assume the metric is asymptotically Schwarzschild, from this moment on, you don't have to assume that it is flat with, it must approach it only as a metric, not with any order. We can forget first and especially second derivative, which makes no geometric sense, the dependent coordinate system. You see, being to
Right.
metric close is no nice condition, it's invariant, but saying
Yeah.
that close with some order is just
Mm-hmm.
artifact of coordinate system,
Mm-hmm.
right?
Mm-hmm.
And so my question is, what is a true theorem? What is invariant you have to write down? What would be different, probably slightly different concept of a mass to incorporate both results?
Yeah. Yeah.
I mean, I would imagine the limit of the Hawking mass, that's coordinate independent.
But would Hawking map have this property? All these derivatives come there?
Because it's the mean curvature term. It would be only the mean curvature.
Yeah, it will be on the mean curvature. So, but again,
Yeah.
my question is, yeah, there is this mean curvature, but the question is, if then you still need second derivative of the metric.
Yeah.
So first derivative
I think
can
it's just
accept.
first derivatives. I think ultimately it's just first derivatives. Integrals of first derivatives.
So you can throw away second derivatives.
I believe so.
Yeah, because if it is Schwarzschild, you don't even first derivative.
Mm-hmm.
I think if you integrate our annuli, then you also only need first derivatives.
In the definition of asymptotically flat.
Right. Yeah. I think essentially some first derivative information is needed, but it's a question whether, yeah. I don't think you really need second derivative information, but yeah. And that's a great question. I don't have it's a very stimulating question, but I don't have an answer for that.
Mm-hmm.
Okay.
And it's great for, yeah, formulating the
Because mean curvature corresponds to the first derivative.
Yeah,
Right.
yeah.
Yeah. So should I move on?
Yeah.
Okay, yeah, excuse me, yeah. Just,
Okay, yeah, thanks. Okay. Yeah, so as I mentioned that this quantity is well defined that follows from the asymptotic condition together with the integrability scalar curvature. So that's where the integrability is needed, and also it depends only on the metric and not on the coordinate chosen. Okay. And also, why is it called a mass is because for the like a very nice metric, Schwarzschild metric, describing the gravity generated by point mass, this definition agrees with the mass that was given, the mass of the point mass, and therefore it makes sense to call it mass. All right, so now the classical positive mass theorem is as follows, that if you have a asymptotic flat manifold, either the dimension is between 3 and 7, or the manifold is spin, then the non-negative scalar curvature implies the non-negative mass. And moreover, one has the rigidity, namely the mass equals 0, if and only if the space is the Euclidean space, is isometric to the Euclidean space. So this positive mass theorem was first proved by Schoen and Yau in 1979 for dimension between 3 and 7 using minimal surface techniques. And then later Witten proved it for spin manifolds in 1981 using Dirac operators. And so here, physically, scalar curvature should be interpreted as some kind of a local mass density. So what the theorem says in physical terms is that if the local mass density is non-negative, then the total mass is non-negative. So the mass here describes the total mass contained in the space, which is intuitively quite clear, but of course the proof is not. All right, so this remarkable theorem has a lot of significant consequences, and one of them is so-called the Garrosh conjecture, which we'll just talk about a moment later, and it's also related to a series of scalar curvature rigidity theorems. And also, it's one of the significant application is Schoen's final resolution of the famous Yamabe problem. And it's also used in Bray's solution of the Penrose inequality, as well as some so-called black hole uniqueness theorem. As I mentioned, that the two approaches by Schoen-Yau and Witten, respectively, they use quite different methods, minimal surface and Dirac operators. Okay, so the connection with the positive scalar curvature metric is from the Schoen-Yau's approach together with the observation by Low-Kemp. So roughly speaking, if you start with an asymptotically flat manifold with non-negative scalar curvature but negative mass, you can construct a positive scalar curvature metric on the connected sum of the one-point compactification of the asymptotic flat manifold with the torus, okay? And as a result, this is the proof of positive mass theorem is reduced to proving that this connected sum has no positive positive scalar curvature metric. And this is referred as the Garrosh conjecture. Okay, so before I state the Gersh conjecture, let me also indicate by this picture. So you start with the asymptotically flat manifold with the non-negative scalar curvature, but the negative mass. Then you can actually construct a positive scalar curvature metric on this connected sum. Okay, and the basic picture is topologically you can draw at infinity your space is asymptotically Euclidean, looks like Euclidean space. So you can draw a big box, and then you can identify the opposite side of the box. That's where the torus appears. However, inside you have this big bump here, and this big bump will be carried, and that's exactly where the connected sum comes to with this with the 1-point compactification. Okay, so that's the sort of schematic explanation. Of course, you need to construct corresponding metric on this connected sum, and that's the hard work. Okay, any questions about that? All right, so the so-called Gersh conjecture is exactly saying that for any closed manifolds, M1, the connected sum with the torus has no positive scalar curvature metric. And this is proven for low dimension, the dimension less than or equal to 7 by Schoen-Yau, and then for spin manifolds by Gromov and Lawson. There's a generalization of this conjecture because in the previous consideration, you can also allow multiple n, not just the asymptotically flat end, but you can also have other end. And in this case, the other end will carry over to connected sum, and then you end up with a non-compact manifold in that setting. Okay, so it makes sense to allow non-compact manifolds. And so that's usually referred as the generalized Gersh conjecture, which states that for any, so you don't require closed manifold, for any manifold M1, the connected sum with the torus has no complete positive scalar curvature metric. And so that's a more settled more recently by Childish and Lee for low dimensions 3 and 7 between, and then by Wang and Zhang for spin manifold.
Yeah, may I make a remark? Of course, now
Yes.
up to dimension 10, at least definitely up to dimension 8.
Yeah,
It follows from
I should also say the previous
dimension 9 and 10. I didn't check carefully, but 8, of course, follows automatically.
Right. Yeah, exactly. Thanks for the remark. Okay. Any other questions or comments for this part? Oh. Okay, so now we're moving to the second part, namely motivations for singular metric. Okay, and there has been a lot of activities in extending positive mass theorem and also positive scalar curvature results to singular metrics. And the motivations for them mainly comes from Gromov's program. Okay, so Misha has this program in extending in defining a weak notion of scalar curvature, just like the same for Ricci curvature and sectional curvature. And in Misha's program, one uses singular metrics. And specifically, Gromov's polyhedral comparison, and this is where a lot of progress, significant progress are made. We mentioned only Chao Li, and then Wang, Xie, and Yu, one of the organizer here, and then Brendo, and so I apologize for the misordering here. So Bear, Brendo, Hanke, and Wang. Okay. Other motivations comes from studying stability problem for the positive mass theorem, most significantly conjecture formulated by Somani and Gromov. And so in those problems, one considers convergence problems, and but under weak scalar curvature bound, and so you're bound to run into singularities. And also, as we'll see, the singularities naturally occur.
Maybe I comment Dan Lee should be given a lot of credit on the stability problem for PMT.
I see. Okay.
Just to be, yeah.
Right.
Dan Lee there. Yeah. Thank you.
Okay. Yeah.
LEE.
LEE. Okay.
Yeah.
Okay. Thanks for the comment. All right. So talking about one specific instance where singularity singular metric explicitly occur is what people refer as Schoen's conjecture. Basically, Schoen's conjecture wants to investigate how much singularities will influence the so-called Yamabe type of the space. So more specifically, you look at the closed manifold, but you're assuming that the closed manifold has no positive scalar curvature matrix. In other words, this can be said simply that the Schoen sigma constant is less than or equal to 0, so it's non-positive. And then you consider a singular metric on your space, and assuming what's called the uniformly Euclidean metric. That basically means it's quasi-isometric to a smooth metric. Okay, and you assume that the metric is non-negative scalar curvature on the smooth part, and moreover, the codimension of its singular set is at least 3. Okay, then Schoen's conjecture says that you don't have singular metric. Actually, the metric is smooth, and as a result, it should be Ricci flat. So basically, codimension 3 or higher will imply it's smooth. It doesn't curve for these spaces. And the reason for there are many reasons for codimension 3 or higher, but one of the obvious reasons is if the codimension is less than or equal to 2, then the obvious examples, counter examples. So, for example, codimension 1, you can just take a cylinder, which is like a football, like a cutoff by the cone part, and then you glue together, and you get obviously counter example in this case, and then codimension equal to 2, you just don't chop off the conical part of your football and then glue the cone together, conical point together. Okay, and so for the Schoen's conjecture, there are already progress. So Lee, Montolides, they proved it for dimension 3, and then Cazares established for dimension 4 for a large class of this kind of manifold, which are introduced by Gromov-Lawson, called the enlargeable manifolds. Okay. And also I should like to mention that the code emission bigger than or equal to 3 reminds us of this famous result of Lawson and Schoen-Yau, which says that code emission 3 or higher surgery preserves positive scalar curvature metric. Okay, so that's the Schoen's conjecture. And then I like to discuss one particular example where singularity actually occurs, but it's for negative mass structural metric. And so this is a well-known negative mass structural metric. In picture looks like this. You have an asymptotic end, and then you have some kind of singularity. And explicitly in dimension 3, it's conformal to the Euclidean metric. And the conformal factor is this 1 minus 2m over r raised to the 4th power. And so this is defined on the ball radius, outside the ball radius 2m, where we're assuming m is bigger than 0. And you can see that asymptotically at infinity, it looks like a Euclidean space. But near the ball radius 2m, the metric actually looks like this. Looks like so effectively this sphere is collapsed to a single point, and then if you measure the distance, sigma is the distance to this singular point, then the metric can be written as d sigma plus a constant times a power of sigma, which the power is 4/3, okay, and then times the standard spherical metric on S2, and then plus high order terms. So also the scalar curvature is identically 0. So this is an example where singularity occurs, and moreover the mass becomes negative. So this introduces us the notion of horns and cones. So this is an example of horn singularity. And the model is as follows. You take a Riemannian manifold n, and you fix a power, let's say b, to be bigger than 0, and you consider the space, which is topologically just product the real line with the n, but the metric looks like a dr squared plus r to the 2b, and then times the metric on n. Okay, so then the metric will basically look like this. And this is what we call the model r to the b horn, if you want to be specific about b, the power. And this, the negative mass structure here, you would have b equals 2/3.
Mhm.
Okay, and also for the specific case when b equals 1, we would call it the model cone. Okay, so and the n is called the will be said to be cross section of such a singular model, and any singularity modeled on these will be called r to the b horn singularity, or or just simply conical singularity if b equals to 1. Since I'm giving the survey talk, so I won't be giving the detailed definition. Changliang in the second talk will tell you the precise definition of these spaces. But roughly speaking, you have an asymptotic end, and then you also have like spikes grow inside, which are modeled on these horns or cones. Okay, so that's the basic picture. Any questions about that? All right, then let's move on. And so here are our basic, basically our main results. Basically, we proved that the positive mass theorem still holds for finitely many conical singularities. So your space can look like asymptotically flat at infinity, but inside you can have finite many conical singularities. Then if the scalar curvature is non-negative on the smooth part, then the mass is also non-negative. Okay, so here we also need to assume either dimension is between 3 or 7 or the manifold spin. Okay. Moreover, we have the rigidity result that if the mass is equal to 0, then that means your space is actually isometric to the Euclidean space. So in other words, if you do have honest conical singularity inside, that's going to force the mass to be positive. Okay, so that's going to give non-trivial contributions to the mass.
Excuse me, may I ask you, in your
Yes.
cone, the base of the cone is supposed to have positive scalar curvature or not?
Very good question. We don't. I mean, effectively, as you may, it's actually because the non-negative scalar curvature assumption on the whole space, the smooth part of the space, that forces the scalar curvature of the cross section to be bigger than or equal to the scalar curvature of the sphere. So that's the
okay. So, but once you have this
assumption.
condition, yeah, but once you have an actual cone, right?
Yeah.
If you forget about rigidity, which is more delicate, if there is no rigidity, then you always can open the cone and make infinite cusp, right? And then it reduces to complete case, right?
Exactly. That's how the proof goes. Exactly.
But this is this is clear. The subtle point, of course, is rigidity.
Yeah. The rigidity.
Rigidity is the issue. This is standard construction, but the issue, of course, in the rigidity.
Right. Yeah. Okay. Right. Yeah.
So this is kind of standard. I mean, everybody knows that. But if you don't care, but rigidity is a new ingredient, new stuff. And with Horn,
okay. We did work a little bit on constructing the blow-up function.
No, but this is our construction with Lawson. You apply this construction to any conical metric.
Yeah, exactly.
This is a construction. Yeah, used everywhere.
Okay. Yeah.
But the rigidity.
Right. Yeah. Rigidity. Yeah. Okay. So I'll indicate what's involved in both situations. Okay. Thanks. All right. So similarly for Horn singularities, we also have positive mass theorem, and here we need to assume that the space is spin, and also the power here is strictly bigger than 1. Okay, so I mean, you can say bigger than or equal to 1 because conical is covered in the above result. And also, in addition, the Yamabe invariant of the cross section is positive. Okay, so that's a sort of a difference from the horn and the cone. So you don't get the Yamabe invariant or the positive scalar curvature on the cross section.
So do you mean the conformal Yamabe invariant or the smooth
the
one?
conformal Yamabe invariant.
Ah.
Exactly. Yeah. Yeah. Okay. Thanks. All right. So let me indicate some of the previous works, and that there's a lot of people, and so for singularities, and I should say that here up to Lee Montalides, they're all concerned about continuous metrics. Okay, so roughly speaking, the space has no singularity, but the metric has singularity, and they're concerned about the Sobolev type of regularity for the metric, so you have Graham Tosati and Dan Lee and Shi Tan and Lee LeFloc, and in Lee LeFloc, they managed to deal with the W1N log Sobolev inequality, Sobolev regularity, and moreover, they introduce a distributional scalar curvature, and then they have a positive mass theorem in that case. And the most recent, Zhang, Shen, and Zhang, they also have Sobolev regularity, and so in Lee Montalides, they deal with the conical singularity along codimension 2 submanifold. Okay, and the last two, they have we do have a topological singularity. So this is a physicist. He motivated from black hole, the study of black hole. He considered the conical singularity, but with the non-negative Ricci curvature, improved the positive mass theorem, but without the technical details. And the non-negative Ricci curvature in his setting is kind of natural. And then Zhu and Vyakovsky, they worked for the orbifold singularity. So these two, the situation where the space could be singular, space could have singularities. Perhaps it is also appropriate place to remark here that first of all, conical singularity just spells the weakest Sobolev regularity here, what's called W1N log. Okay, and secondly, conical singularity, because the cross section need not be sphere. So it doesn't have to be the sphere. And that means we have the space has a topological singularity. Okay, so that's the two difference between conical singularity, our work, and the previous work.
Mm-hmm.
Okay, and also I'd like to point out the very interesting work by, first of all, by Bray and Miao, and then later generalized by Miao in dimension 3. I think Penz and Miao also give a talk in this seminar. They have a very interesting so-called mass capacity inequality, and using that mass capacity inequality, one can imply the positive mass theorem for the R to the B Horn singularity, and with the optimal, the power is bigger than 2/3, just like the negative structure, and with some additional topological condition. But the crucial thing is that their mass capacity inequality is only for dimension 3. Okay, and also I should mention the very interesting work of Bray and Jaguar, where they introduced what's called the zero area singularity and prove a positive math theorem incorporating contribution from the singularity. But assuming some conjecture in conformal geometry holds, which is still quite open. All right, so that's the quick overview of previous work. And finally, we also have a Garrosh type theorem for conical singularity. So in other words, for simplicity, I state the simplest version. So you take a closed manifold of dimension bigger than or equal to 3, and assume either you're in a low dimension, so less than 7, for example, or the manifold is spin, and then the connected sum of your manifold with the torus has no positive scalar curvature with conical singularity. So in other words, you allow the metric has conical singularity, but still, in this case, you cannot find a metric with a positive scalar curvature. And moreover, any such a metric with conical singularity and non-negative scalar curvature must be smooth and flat. Okay. So that this will be a sort of special case of Schoen's conjecture. But more generally, we actually allow topological conical singularity. So that's in the full generality, we actually allow so this can occur, for example, if you take this manifold to be manifold with boundary, and then connect the sum with the torus. But then the metric will have to pinch the boundary to a single point. Then you're getting an honest topological singularity. So this will be one situation that could occur. And so our result also applied to this case. Okay, so how much time I have left? I'm not sure.
I think you have
Maybe
5 minutes.
Okay, thank you. So let me try to finish, or I'll just indicate the ideas proof. So as Misha pointed out, so maybe this is a fairly standard modular, some kind of technical details. So basically, it's some idea going back to Schoen's work on Yamabe problem. So basically, you wanted to consider another metric which is conformal to your original metric. So I've drawn the picture of the original metric with the conical singularity here. And the key point is that you wanted to solve the harmonic function U, where the harmonic function is having like a Green's function where the pole at the conical point. So it blows up like a Green's function 2 to the r to the 2 minus n as you approach in the conical singularity, and then it's approaching 1 at infinity. Okay, so and if you do this conformal change, I've drawn the picture here, this is going to invert the cone and makes it from incomplete cone to asymptotically conical cone. Okay, so now it becomes complete. So that's the basic idea. And then you could either apply some results of a Hersch-Miao for manifold with boundary or you apply some recent result by Lesud, Unger, and Yao for complete matrix. And this will give you the non-negativity of the mass. Okay, so the mass is going to be changed, but only slightly. So you only need to do another change, and that's going to make this constant to be as small as you want, and therefore the non-negativity of this mass implies non-negativity of that. Okay, so this is the proof for the positive or non-negative part of the proof. And then for the rigidity, you first go the usual route and starting with the starting with the zero mass, and you actually end up showing that the Ricci is identically zero, and that shows that the Ricci curvature of the cross section has to be the Ricci curvature of the sphere, which is m-2. And then you construct the asymptotic harmonic coordinate, and the asymptotic harmonic coordinate will have, you prove that it will have this expansion. So basically like a constant times r to the some power, and times, this is where you use the model cone, and then the power here involves the first eigenvalue of the Laplacian on the cross section, and the eigenfunction also appears here. And so by the Nishinovitz eigenvalue estimate, you know that the eigenvalue of this first non-trivial eigenvalue will be bigger than or equal to n-1. That implies that the power here, alpha, is bigger than or equal to 1. And then from Bachner's formula, and then together with the mass equal to 0, you can deduce that the dyi will be parallel. And that's going to force your power to be exactly 1, which means that the first eigenvalue will have to be exactly n-1. And then you can apply Obata's rigidity result to deduce that the cross-section will have to be the standard sphere. Okay, so this is Obata's rigidity. And then you actually deduce that in this case, the metric will have to be in the Sobolev W1n, and therefore we can apply the result of Jiang, Shen, and Zhang, and to conclude the rigidity. So that's the outline of the proof. Okay, I think it's a good time to stop here. Thank you very much for your attention.